Alright, so in case you missed the explanation of this lab, I'm going to go through it ahead right now. And this is lab 1.7, the projectile launcher lab. And again, the purpose or the idea of this lab is if I have my lab table and I have a projectile getting fired off the side of the lab table at some height, I'm trying to figure out the distance that it goes. And I place my target wherever that distance is going to go. The problem is this is a very complex problem because I don't know, or you didn't know until the day of testing what this angle is, and therefore it's really hard, but you need to solve for what this delta x is. Okay, so that's the main concept of the lab. And in order for us to do this reasonably, I have to start with a simpler type of problem. Instead of me worrying about the angle that the projectile is going at, I am instead going to start with a flat angle, meaning an angle of 0 degrees, and that path is going to be a little bit different. But the nice thing about this is my VI in the y direction equals 0 meters per second. My VF in the y direction, I don't know, but my YF, my displacement in the y, or my final position in the y is going to be 0 meters. So this is actually similar to our first type of problem, which is the projectile getting shot straight off the side. And for that, I can use my special case formula that we talked about and we derived, and that's that the time down is equal to the square root of negative 2yi over g. So that is going to help me get my time down for the first half of this problem. The other thing that I can measure is my displacement. So that's my delta x from the lab station or from wherever it was launched all the way to the edge. And for that, I have that my delta x equals my velocity in the x direction times the time. Well, if I'm solving for the velocity in the x direction, that's Vx equals delta x over t, and conveniently, that is the velocity in the x direction right here when it leaves, because it's always the velocity in the x direction. And if I always have the velocity in the x direction, then I can use that as essentially my initial launching velocity. So that's the velocity that the projectile actually leaves the projectile launcher, which is what I need to solve for any angle looking in the actual, when I'm looking for to actually solve my problem. So that's like the first big thing. And the only thing that it requires me to do is I have to measure the height of the lab station. I'm sorry, the height not only of the lab station, but of where the projectile launcher is above the lab station, because that's not negligible. There's enough there. And then I need to do a couple test firings, and I need to see exactly where the projectile lands, and I'll want to do probably 4 or 5 trials of that, but that'll help me get my delta x, and if I use those two things, then I can solve for my, essentially what I refer to as my escape velocity or my projectile velocity when I fire that projectile for any type of problem. Okay, alright, so I'm going to continue this problem, and now I'm going to assume a couple things. So I'm still trying to solve for this displacement here when I'm firing at some initial angle, but I'm going to assume now that I have the initial velocity. And that initial velocity is not the velocity of the x direction or the y direction, that is just the velocity that my projectile launcher fires at. And it doesn't matter what angle it's at, it doesn't matter if it's on a lab station or not, all it matters is that's what my projectile launcher fires at. So now I'm going to assume that I have an angle. So the first thing I need to do, if I'm solving for the displacement, which I have right here, well, my very simple formula is that my displacement, my delta x, equals the velocity in the x direction times the time. Well, going back to my initial velocity always represents the hypotenuse of this, because that's whatever I'm fired at, and then I have an x component and I have a y component. So this is Vx and this is Vy, and my angle is right in here. So my velocity in the x direction is going to equal V times the cosine of that angle. And if I go back to my formula that's over here, I can actually plug that in right away, and I can say my delta x equals the velocity times the cosine of my angle and then I'm still worried about the time. And in this case, I'm going to change colors here, and I'm going to divide this problem up. There's the time that it takes to go up, and the time that it takes to go down. And that's going to be the sum, so my total time is the time up plus the time down. So I know that. I have all that. I'm good to go with that, conceptually at least. So my time down is going to start from my new height, and my time up is going to be for whatever it takes to take from that projectile launcher up to the new height. And that is completely dependent on the velocity in the y direction, the initial velocity in the y direction. And the initial velocity in the y direction, so Vy, is going to equal V times the sine of my angle. So V sine of angle. And I can't really do much without picking some numbers up for that, so I'm not going to go through and solve all that right away. But conceptually speaking, I have my Vy. That's my Vy initial. That's my initial velocity. And the time that it takes to go up is going to be when that initial velocity gets to 0. So my final velocity is going to be 0 meters per second, and that's, again, that's at the very tip top of this projectile. So my acceleration equals g equals negative 9.80 meters per second squared, and I can use equation 4 to solve for the time that it takes to go up. And that'll of course be t equals, well, it's Vf equals Vi plus At. Vf is 0, so it's negative Vi divided by A, or in this case A is g. So I can get the time up with that equation. So I'm going to go ahead and get rid of all this and know that I've now solved for the time up. So I have time up. That is a check done. Cool. So what I'm worried about next is the time down. And the time down is actually really easy because that's going to use that special case equation that I had. Unless I'm accounting for the cups, that's a side conversation, but the time down is going to equal the square root of negative 2 times the height initial over the gravity, the acceleration due to gravity. So that's my formula for the time down. So that's going to go into the second half of this little time equation. And what it requires is whatever for me to know what this new height is. So now, if I have the time up already, I can solve it using equation 5. Or if I don't have the time up, I can just know that this is Vf right here, and that's 0, and this is Vi, and that's going to be the V times the sine of the theta, and I can use equation 6, which is going to be Vf squared equals Vi squared plus 2a delta y, and I can use that to solve for my change in height. I add that change in height to my initial height because I'm increasing from the height of the projectile with the launcher to the new height, and that new height is going to get plugged in right here, and then I use that to find the time that it takes to go down. Once I have time down, I'll put a little check here. I can add those two times together, multiply that by my velocity in the x direction, which is v times the cosine of whatever angle I have, and that will equal the displacement, how far that projectile will launch. Now, I need specific numbers in order to really solve this, so I'm going to do an example problem in another video, but this is how you can solve it algebraically, so it should give you a little bit of background information. So the next video will have this being solved, but it'll be going less discussion and more just getting it solved.